This is second half of lecture 19. In this recording, we will continue discussing angular momentum. More specifically, we will look at cases when angular momentum is conserved, and we will see how that the conservation of angular momentum helps us figure out how things work. So when is the angular momentum conserved? If you remember the equation that governs change in angular momentum, that equation tells you that torque is equal to the rate of change of angular momentum. And from here, it follows that if there is no torque, or if the net torque is zero, then there is no change in angular momentum, so the angular momentum as a vector will be conserved. So we say angular momentum is constant. Now, to remind you, angular momentum, if you have an object and this object rotates, its angular momentum is its moment of inertia times its angular speed. So if something happens to this object, for example, to its angular momentum, if somehow this object changes shape and its moment of inertia goes up, then the speed of rotation must go down because the angular momentum is conserved, and the other way around. If the moment of inertia goes down, then to preserve angular momentum, the angular speed of rotation must go up. A good example of this, a good demo of this is a skater. I'm now on slide number 6. So imagine a skater who is spinning. Let's say she's spinning counterclockwise like so. And if you have skated, or if you have watched figure skating or ballet, you know that if this skater brings her arms and her leg closer to her body, kind of like this, she will continue spinning, but she will continue spinning faster. So her angular speed will go up. Now, to understand why that's happening, we have to look at the conservation of angular momentum. The skater is kind of a closed system. When she brings her arms in and her leg in, that's not because of external forces. Those forces are internal. And if there are no external forces and no external torques, then we know that her angular momentum must be conserved. So let's think about what happens to her moment of inertia when she brings her mass closer to the axis of rotation. You probably remember that if you have a point particle rotating, then its moment of inertia is mass times radius squared. So basically, this equation tells you that if you get closer to the axis of rotation, your moment of inertia goes down. And for extended objects, you have different formulas. For a sphere, for a solid sphere, for example, you have, I think, 2/5 of mr squared. But even for extended objects, if your mass is closer to the axis of rotation, your angular moment of inertia goes down. So when the skater does this, her moment of inertia goes down. And since there are no external torques, the angular momentum must be conserved. And to conserve the angular momentum, the speed of her rotation must go up. And that's generically what happens to objects that spin. If somehow you spread out their mass they will slow down. And if you bring the mass in closer to the axis of rotation, they tend to slow down. Now, what I would like to do is I would like to solve a few problems that involve conservation of angular momentum to give you a flavor of how this concept could be useful in practice. The first problem that I want to look at is on slide number 7. It's a collision where you have a bullet, and this bullet is fired at a block that's suspended on a rod. And this is the pivot point up here. And so if the bullet gets stuck in this block, we know what happens. This block swings up. And this problem is kind of similar to the problems that we had before. I think we even had one on exam 3. The difference here is that what we had before was this block suspended on a string, and the string was really, really light. Instead, we have a rod here, and the rod is different from a string because it's heavier. It has non-negligible mass. So when the bullet gets stuck in the block, it doesn't only move the block, it also starts moving the rod. And so now the question is, how high will this block go? Let's see how we can solve this problem using the concept of the conservation of angular momentum. So let's divide this problem into 2 stages. Stage 1 is the collision and bullet getting stuck in the block. And since there are no external torques, there is gravity here, of course. Gravity is acting like this. But if you look at the force of gravity, it's aligned with the position vector coming from the pivot point. So in this case, at the lowest point, gravity provides no torque. So we can ignore it. And we can say that as the bullet gets stuck in the block, there are no external torques. So if that's the case, then angular momentum is conserved, and angular momentum in the beginning is equal to the angular momentum at the end. Beginning being just before the collision, and final position being after the bullet gets stuck. So let's think about the initial point. The bullet is now here. It's just about to enter the block. What's the angular momentum? Well, this bullet can be approximated as a particle because it's small. And for particles, we know that angular momentum is mass times r, where r is this distance, times v, where v is initial velocity of the bullet. And once this bullet gets stuck in the block, now we have 3 objects moving on this circular path. One object is the bullet, and the bullet will have angular momentum of m r v final. Then we have this block. Okay, we have this block, and the angular momentum of the block will be mass of the block times r times velocity, and the block has the same velocity as the bullet because the bullet is stuck in the block. And then in addition, we will have this rod, and the angular momentum of the rod will be I of the rod times angular velocity of the rod. Before we continue solving this problem, we have to figure out what these 2 are. Let's start with the moment of inertia. When I look in the table where I have lists of moments of inertia for basic shapes, I see that if I have a rod, and if this rod is rotating around one of its ends, then the moment of inertia is 1/3 of its mass times its length squared. And the length, in this case, is the same r. So it's very important that we use the right formula. There are two formulas in the list in the table. One formula is for the rod when the pivot point is at one of its ends, and one formula is when the pivot point is in between. So it's important that you use the right formula. Okay, so this is the moment of inertia. And now for the angular velocity, we will use this familiar formula. You know that the linear and the angular motions are related in the following way. Velocity linear is velocity angular times r, which means that velocity angular is velocity linear divided by r. So I will use this formula here, since the rod is moving with the same, this end point of the rod is moving with the same velocity as the block and the bullet. I will write it's V final divided by R, and one set of R's will cancel out. So my conservation of angular momentum, finally, after all of this, reads M mass of the bullet times R times V initial is equal to M times R V final plus mass of the bullet, mass of the block times R times V final plus 1/3 of the mass of the rod times R times V final. And from here, I can solve for V final. My V final will be M R V initial divided by M R plus M of the block times R plus 1/3 M of the rod times R. And it looks like I can also cancel out R. I will cancel out R on top and on the bottom, and I will have the simpler formula that will tell me how fast my block plus the bullet plus the rod are moving just after the collision. So let's look at this formula. Let's analyze it. Let's see if it makes sense. So this formula tells me that if I have higher initial velocity of the bullet, I will have higher final velocity. That kind of makes sense. And it also tells me that if my block is really heavy and if my rod is really heavy, then I will have lower final velocity, which also makes sense. Now, the difference between this and a simpler case when I had a rope that was really, really light is that I have this extra term. And so you see, because I had a rod that had some mass, my final velocity is now lower, which also makes sense. To find out how far this will go up, I will have to use the conservation of energy. I will compute my initial energy here, and then I will compute my final energy here. I will have some MGH. I'm not gonna solve this in this video recording. I will leave it up to you. If you get stuck with this, please join our Zoom help room sessions on Monday, Wednesday, and Friday at 12:30, between 12:30 and 2:30. So one question you may be asking is, why can't I use conservation of linear momentum when I had this rope? I just used conservation of momentum and that kind of worked for me. So why can't I do exactly the same thing here? Why do I have to use the conservation of angular momentum? And the answer to this question is that you don't really have to use the conservation of angular momentum. You could use the conservation of linear momentum, but then things would be trickier because you have this extended object, which is the rod. And to use the conservation of momentum, what you would have to do is you would have to divide this road into small chunks. And for each chunk, then you would have to write whatever the momentum of this chunk is. It would be mass of this piece times velocity of this piece. And then you would have different velocities because things that are closer to the pivot point would be moving slower. And if you did this, then this would work and this would probably give you the same result. It's just less convenient. And by using conservation of angular momentum, you are now allowed to treat this rod, even though it's an extended object, you are allowed to treat it as one object. Let's now move to the next problem. This problem is on slide number 8. And this is a problem where you have, what do you have here? You have a moving disk. So you have this disk. And let's say this disk has some mass m. And they tell you that a cat is sitting at the edge of this disk. Let's say the mass of this cat is m small. The radius of the disk is r2, and this disk is spinning with some angular velocity omega. As this disk is spinning, the cat starts moving, and it moves towards the middle until it reaches a position where it's now distance r1 away from the middle. And the question is, how fast is this disk moving now that the cat has moved? So first of all, I would like you to pause and think about whether you think this disk will move faster or whether you think it will move slower. The answer is that it will probably move faster. And that's because we know that angular momentum must be conserved. There are no external forces. There are just forces between the cat and the disk. Those are internal forces. So my initial angular momentum must be equal to my final angular momentum. Angular momentum is moment of inertia times angular speed. And when the cat is moving closer to the axis of rotation, the moment of inertia goes down, which means that we expect angular speed to go up because that's needed for conserving angular momentum. So let's actually solve it. Let's write out all the equations. In the beginning, I have two objects spinning with the same angular velocity. I have my disk. And for the disk, my angular momentum is moment of inertia of the disk times angular velocity of the disk. Plus I have a cat. And since this cat is small, I will approximate as a point object. So I will write that angular momentum of the cat is mass of the cat times distance from the origin of the cat times velocity of the cat. And towards the end, I have kind of the same thing. My disk didn't change, but its speed is now different. So I will denote the new angular speed by omega prime. And I have the same cat, except this cat is now at a different position and it has a different velocity. So this is my conservation of angular momentum. What I want to do is I want to find my omega and my v. Now, one thing I will do is I will use the relationship between linear and angular speeds. I know that linear speed is angular speed times r. So what I will do is both here and here, I will replace velocities, linear velocities with angular velocities. So in the beginning, I have I of the disk times omega of the disk plus mass of the cat times R2 times omega, and this omega is now the same because the cat is sitting on the disk, times R2. I will combine these two R2s to make R2 squared. And towards the end, I have a similar equation, ID omega prime d plus mass of the cat, and I will get, again, if I use this equation, I will get R1 squared times omega d prime. And this now I can solve for omega d prime, and I get my new speed, angular speed, to be equal to I d plus mass of the cat, mass of the cat times R2 squared divided by ID plus mass of the cat R1 squared times old angular speed. So this is my solution. Many terms are identical here except for this R2 and R1. R1 is smaller. This means that I'm dividing a bigger number by a smaller number. So I will get something that's more than 1, which means that my new speed, my new angular speed is higher than my old angular speed, which makes sense. Okay, now I will move to the next problem, which is on slide number 9. This is a problem where you have changing mass. And in this problem, which I copied from your textbook, you have a vinyl record. It has a mass of 0.1 kilos. It has a radius of 0.1 meters. And it rotates with an angular speed of 4.7 radians per second. They also tell me that the moment of inertia of this is 5 10 into negative 4 kilograms times meter squared. And then they tell me that I have a patty of mass 0.02 kilos, and it's dropped vertically onto the record, and it sticks to the edge. The question is, what's the angular speed of the record immediately afterwards? So first of all, let's think about what we think is happening here. I want you to pause this video and think whether or not you expect the speed of this vinyl record to go down or to go up. So the question was, do you expect the speed to go up or go down? And I think we expect speed to go down because we know that moment of inertia is conserved, angular momentum is conserved. Angular momentum is moment of inertia times omega. And by making our disk heavier, we kind of increased its moment of inertia, so its angular speed must go down to conserve angular momentum. Okay, so let's write down conservation of angular momentum. Angular momentum in the beginning is equal to the angular momentum at the end. Let's start from the beginning. In the beginning, we have this rotating vinyl record. It has a moment of inertia of 5 10 into the minus 4, and the angular speed of 4.7. So this times that is its angular momentum. Now let's think whether or not this patty has any angular momentum that we care about as it's being dropped. So this is kind of a subtle point. It may not be obvious at first, and I don't have a lot of time to discuss this, but if you have any questions about this, please join my Zoom help room. But what I want to argue is that since this patty, since my vinyl record is only free to rotate around this axis, and this patty is moving initially along parallel this axis, the patty doesn't really have any angular momentum that's relevant to us. So if the patty was moving like this, it may have had some angular momentum that's relevant to us, or if the vinyl was also able to rotate like this, then the patty would have some angular momentum that's relevant to us. But since this is the fixed axis of rotation, and since the motion is parallel to it, we can just ignore the motion of the patty, and we can say that it doesn't have any angular momentum that's relevant to our problem. So in the beginning, the only angular momentum is the angular momentum of the vinyl record. Now, after the patty drops, now both the patty and the record rotate with a different speed. So for the record, we have the same angular momentum, 5 10 to the minus 4, times a new angular speed that we don't know. And for this patty, we have its mass, its distance 0.1 meters away. So the mass is 0.02 kilos. It's 0.1 meters away, so 0.1 squared, times the new angular speed that we don't know. My only unknown in this equation is the new angular speed, and the new angular speed works out to be 5 10 to the minus 4 times 4.7 divided by 5 10 to the minus 4 plus 0.02 times 0.01. So this will be, let me compute it approximately. This is approximately 5. 5 times 5 is 25, so I have approximately 25 10 to the minus 4. And here I have 5 10 to the minus 4 plus 0.0002. So this is 2 10 to the minus 4. So I have approximately 25 10 to the minus 4 divided by 7 times 10 to the minus 4. And this is approximately 25 divided by 7, which is approximately 3.5. So I will leave it up to you to compute the exact number. But from this approximate calculation, it looks like the new angular speed is somewhere in the neighborhood of 3.5 radians per second. It's lower than the original angular speed, which is what we expected. Okay, and finally, I want to look at one problem that's kind of different, but also useful. In this problem, you have two disks that are interconnected, kind of like gears, with a belt. They are connected with a belt. And they tell us that this bigger disk is 3 times as large. So this radius is 3 units, and this radius is 1 unit. Now, if the belt isn't slipping, then we know that the velocity at the rim of both of these disks must be equal. So linear velocity at this point, let me call this point B, must be equal to the linear velocity at this point. Let me call this point A, which means that the angular momentum of B divided by the radius of B must be equal, multiplied by the radius of B must be equal to the angular speed of A multiplied by the radius of A. Here I used, by now I hope, the familiar formula that the linear speed is the angular speed times the radius. Okay, so this tells us that W omega A is 3 times omega B, which makes sense. This is what you would expect. This smaller disk is rotating 3 times as fast as this disk. Now the question is, what's the ratio of their angular momenta? And what's the ratio of their rotational energies? So that kind of depends on their mass. So this will be MB, this will be MA. If they have masses MB and MA, I'm not going to specify those masses. Then what I need to do is I need to look up the moment of inertia of a disk. Let me look into the table. I'm looking for a uniform disk. So 10 solid disk of radius R and mass M, when it's rotating around its center, is half of mr squared. Okay, so it's half of mr squared. So for B, I would have half of mb times r squared, which is 3 squared, which is 9. And for IA, I would have half of MA times 1 squared, which is 1. So these are the moments of inertia. Now let's start with the angular momenta. The angular momentum is I times omega. So for object B, I have IB times omega B, which is 9/2 of mass of B times omega B. And for object A, I have IA times omega A, which is half of mass A times omega A. So this is the angular momentum of disk B, and this is the angular momentum of disk A. Now I can, what I can do is I can take the ratio. So ratio of the angular momentum of B to A will be, so if I divide this by that, I will have 9. The 1/2 will cancel out. Mass of B divided by mass of A. And from here, I have omega B divided by omega A. And I know that omega B divided by omega A is 1/3 because omega A is 3 times as large. So 1/3. In the end, my ratio works out to be 3 times mass of B divided by mass of A. So looking back at this picture, it looks like if I want these two disks to have the same angular momentum, then I should make this disk 3 times as heavy as this disk. And then they will have the same amount of angular momentum. Now I can do exactly the same thing for the rotational energy. The only difference is that rotational energy is I omega squared divided by 2 instead of just I omega. So this squared divided by 2 is the rotational energy of disk B, and IA omega A squared divided by 2 is the rotational energy of disk A. I will go quick here because I'm running out of time, but you can kind of pause this recording and think about this at your own pace. So for disk B, I have 9 quarters of mb times omega b squared. And for disk A, I have, what do I have? I have 1/4 of MA times omega A squared. This is energy of disk A. This is energy of disk B. This is energy of disk A. And if I take the ratio of energies, I will get, the quarter will cancel out. I will get the 9, mass of B over mass of A. And what I have here is omega B squared divided by omega A squared. Omega A is 3 times as large. So omega A squared will be 9 times as large. And I will get 1/9. So 9 cancels out with 9. And what I get is that the ratio of energies is the ratio of masses. So if I want these two, disks to have the same energy, I should make them be of equal mass. This is the end of lecture 19. Just to remind you, we went over angular momentum and conservation of angular momentum. You will have quite a few homework problems where you will need to use conservation of momentum. And again, it's very difficult to record the lecture in such a way that it answers all your potential questions. So if you have any leftover questions, if you get stuck with your homework, or if something from here isn't clear, please do join the Zoom help room on Friday from 12:30 till 2:30.